Welcome, everybody. Welcome back to Scaling Networks. And today we're going to talk about chapter number 9. We're going to keep studying OSPF. And today we're going to talk about multi-area OSPF. Now, last week we discussed about chapter 8, which was single area OSPF design. So you basically talked about these extraordinary dynamic routing protocol known as OSPF. We talked about how it works. We talked about the adjacencies, the hello messages, the neighbors. We talked about the protocol that OSPF uses in IP, which is 89. We talked about all the messages that OSPF relies on to exchange information with the neighbors. We talked about the LSDB, the link state database that contains the information about all the links when we have OSPF. We talked about the algorithm that OSPF uses to determine the best path, which is the Dijkstra algorithm that will basically run calculations to find the best routes to certain networks. And we also talked about how OSPF makes decisions of what is considered to be the best route. So OSPF uses the metric, and the metric that OSPF uses is the cost. Now, the cost which is associated to OSPF is just the reference bandwidth over the interface. So the interface bandwidth. So it basically considers just the interface bandwidth. Now, when we discussed about EIGRP, just a recap, EIGRP considers the bandwidth as well. But the biggest difference between EIGRP and OSPF is that EIGRP will also consider the delay whenever calculating the best paths to certain networks. We talked about how the routers communicate when they are part of the OSPF, the same OSPF area. We talked about the multicast messages that OSPF uses to do router communication. We talked about all of this. We talked about the passive interface command. We talked about how to advertise the networks into OSPF. And then we discussed OSPF version 3 and how OSPF version 3 allows us to share IPv6 address information, including IPv6 address networks. So today we're going to continue studying OSPF. So last week we also talked about the hierarchical design of OSPF and the fact that OSPF will allow us to create different areas. And today we're going to find out why the multi-area design, why this hierarchical OSPF design is so important for us. So these are the main topics we are going to discuss. The first one is the operation of multi-area OSPF. What is the major difference for when I'm configuring multi-area OSPF and when I'm configuring a single area OSPF? How does the operation of these two things compare? We are going to explain the multi-area concept, how it operates, and why is it good for medium-sized business networks. We're going to talk about why multi-area OSPF is even used, because so far it's just a general concept. We do have single area, we do have multi-area, but why do we have these sort of things? Why we don't have this in EIGRP, for example. So we're going to discuss that as well. We're going to talk about how multi-area OSPF version 2 uses the link state advertisements. So if you remember the link state advertisements, they are the type of messages that the routers they use to exchange information and so on. So we're going to discuss a little bit more about them and the function of each one of the link state advertisements as well. We're going to explain how multi-area OSPF establishes the neighbor adjacencies, the friendship between the routers, how they establish these adjacencies, and how they keep communicating and exchanging information. The second topic we're going to discuss is how to implement multi-area OSPF. Not only we're going to learn how it works, not only we are going to work why do we even have these things, we are also going to learn how to implement it. You see that the implementation phase of multi-area OSPF is not that much different from configuring single area OSPF. The major difference is just that you have to consider that you have many different areas and that you have to consider that area 0 should be a transit area for all the other areas. So more details later on. So let's keep going. Multi-area OSPF operation. Now, areas in OSPF, they work as a boundary. Okay, so every time you think about an OSPF area, that is a boundary. A boundary for what? A boundary for the link state database. So all the routers that belong to the same area, they will have the same link state database. So what that means is the more routers we have, the more networks we have in the same exact area, the bigger, the larger, the greater the routing table, the bigger, the larger, the greater the link state database as well. And a consequence of this is that we're going to have to share the network information. If all the routers, they are in the same area, they will all have to have the same exact copy of the link state database. So if you think about it, the bigger, the more networks we have, the more routers we have, the bigger the area with more routers, with more networks, the more information we have to exchange, the bigger the link state database will be. The calculations will take longer because now you have more entries in the table and so on. So having a single area OSPF may sound like a good idea, but depending on the size of the network, depending on the size of the area, it may not be a good idea because it's going to slow down the shortest path algorithm. You remember the SPF algorithm? It will do the calculation based on Dijkstra algorithm to find out what is the best routes for certain networks. A consequence of having a larger LSDB, the link state database, is that it's going to take longer for all the routers to converge. Remember, the convergence is the final state where all the routers, they learn about everything, they do the calculations for all the networks, and they are ready to route the packets. To make OSPF more efficient and scalable, what we are going to do is we are going to cut down these areas into separate areas to make sure that our OSPF will operate at its best performance. So if we cannot get away with large link state databases, how about if we separate the link state databases into different areas, different groups? This is exactly what the multi-area OSPF is going to allow us to do. Now, multi-area OSPF, large OSPF area is divided into smaller areas. So instead of having just the usual single area design where all the routers will share the same information, will build the same link state database, our multi-area will separate these messages that the routers exchange. It will separate the link state database into boundaries. And these boundaries are the areas. Now, it requires a hierarchical design, and that is because pretty much all the areas, they have to have a way to area 0. So that basically means whenever we have a router that is part of different areas, one of the areas has to be area 0, because area 0 is known as the backbone area, and area 0 is the area that allows advertisements from one area go into a different area. So area 0 is responsible for advertising areas from different areas into different areas. So for example, in this image that we have here, we have all the 5 routers to the left as part of area 1. We do have router 1 and 2 as part of area 0. And all the routers to the right, they belong to area 51. Now, area 0 is known as the transit area because area 51 still needs to know about the networks in area 1. And what happens is if we connect area 1 to router 1 and then directly area 51 to router 1, we don't have the backbone area in between. And that basically means that the networks that we have in area 1 and 51, they are not going to be able to be shared. They will not be injected. And that is because for routes to be injected from one area into another area, they have to go through the process. And the process is by going through area 0. All right. The advantages of multi-area OSPF, of course, we are going to have smaller routing tables, fewer routing table entries, as network addresses can be summarized between the areas. So you can basically create summary advertisements. So instead of router 1 advertising all the networks that it received from all the routers in area 1, it will just take all of these routes. Instead of advertising them individually, router 1 is able to advertise it as a summary address. So if you remember what a summary address is when we take multiple networks and we combine them into one summary statement, one summary network that represents multiple networks. All right. So with this, we have reduced link state updates as well. So it has less overhead. And with this, we have reduced frequency of SPF calculations, because now every other router outside of area 1 doesn't need to worry about specific areas because it will only see the summary. So it doesn't care, it doesn't need to calculate using the SPF algorithm another route because it only sees the summary. This is an amazing way to reduce the amount of OSPF traffic. This is a great way to reduce the size of the LSDBs. And this is a great way to reduce the amount of adjacencies. We're going to discuss why these adjacencies are important in the next upcoming few slides. OSPF two-layer area hierarchy. Multi-area OSPF is implemented in a two-layer area hierarchy. Backbone, which I just mentioned to you guys, is the transit area, which is area 0. So if you want to share routes between different areas, they have to go through area 0. That's why area 0 is known as the transit area. Regular non-backbone areas, they connect users and resources. They usually set up along functional or geographical groups. All traffic from other areas must cross a transit area. Otherwise, they are not injected. They are not learned. That's why it's very important for us when we are actually analyzing a topology with multi-area OSPF. The key thing to analyze if that's a good design or not is to observe that all the routes, they have to be connected to area 0 somehow. This is one example. Area 1 is connected to one interface of router 1. The other interface of router 1 is being connected to area 0. So area 1 is good in regards to design goals. Now, area 51, the same thing, because we have one interface of router 2 connected to area 51, and the other interface of router 2 is connected to area 0. So this is a good design. All the networks that area 1 needs to advertise, they will pass through the transit area, which is area 0. Now, in terms of terminology for the routers, there's a special name for the routers in OSPF. The router that connects different areas and it has one of the interfaces connected to area 0, this router is known as the area border router because it sits right in the border of areas, different areas. The same goes for router 2. Router 2 is also an ABR or area border router because it connects different areas, right? Now, all the routers inside a single area, they are all OSPF routers, but they are not area border routers. Remember that an area border router will be connecting different areas. There's also one more term that we need to learn, which is the autonomous system border router. The autonomous system border router is the router that the OSPF router that connects our network to something else. For example, the internet. So this router will actually learn routes through the internet as well. And we'll have to go out of the internet interface as well. And if it was connected to another routing autonomous system running EIGRP, RIP, or something else, that would be considered to be a autonomous system border router. Because remember that everything we have in OSPF, even though we have different areas, they are all in the same autonomous system. Because after all, OSPF is only in the same autonomous system. All right. So you guys remember that EIGRP, we actually have to specify the autonomous system number. In OSPF, we have to specify the process ID. And the process ID is locally significant to every single one of the routers. All right? Okay. Types of OSPF routers that we just discussed.
Robert?
Yes, Shai?
Just a quick question. The process ID, just to verify, the process ID, it doesn't have to be similar between the routers in the same area, right?
No, it
It's
doesn't.
just an internal local process that's run on the router and can be different between routers. It doesn't matter, right? As long as they're
Exactly.
the same area.
No, it doesn't have to be the same. Okay.
Okay.
It is a nice practice to assign the same. Just, it's going to be easier for you when troubleshooting things if you assign the same number, but it's not compulsory. Okay. So you can assign a different number. As long as they are in the same area, they're still going to form the adjacency. They're still going to be neighbors. Is that clear?
Okay.
All right. So this is the terminology we just discussed. So we have the area border router, which sits between different areas. We have the autonomous system border router that has at least one interface attached to an external network. The other routers, the one in the same area, they are internal routers. We do have a backbone router, all the routers in area 0 specifically. Now let's do this exercise here. I'm going to ask you guys how many ABRs we have in this topology. How many ABRs, area border routers, do we have here? Yes, we have two. As we already discussed, we have router 1 and router 2. They are both area border routers because they sit in the boundary between different areas. How many ASBRs we have here? Autonomous system border routers. Boundary routers. 1, which is router 1. It's the only one that provides us a way out of the same OSPF routing protocol. Okay. Now, it's important to note that a router can be classified as more than one router type. So router 1 here is ABR and ASBR. Okay. So a router can be multiple things at the same time. Doesn't really matter, right? Let's talk about the message types now, the LSAs, link state advertisement types. We have 1 to 5 in OSPF version 2. In OSPF version 3, we have extra types, all right? Now, we do have 1, 2, 3, 4, and 5 for OSPF version 2. Every single one of these LSAs, they serve for a specific purpose. LSA type 1 will be the router LSA. It's the router advertising the networks that we're basically selecting on the router process. Remember when we go to router OSPF, we type the process ID. Then if we want to advertise certain networks, we type the command network and then specify the network we want to advertise. These messages, they are the LSA type ones that the message will send to let other routers know about the links. Okay, so these are all LSA type 1s, router LSAs. Now, LSA type 2s, they are known as the network LSAs. And these LSA type 2s, they are just to inform what network type we have. So if you guys remember the network type, we do have broadcast, non-broadcast, multi-access, point-to-point, and point-to-multi-point. And we discussed that in a broadcast and non-broadcast multi-access, we do have the election. And the election, if you guys remember, is to designate the designated router, which is basically the master router. Remember that if we don't have the designated router, all the routers, they have to form an adjacency with each other. When we do have the election process, we are going to have the master designated router, which is like the boss of all the other routers. You don't have to become friends with anyone else except the designated router. Okay? So the other routers, they will just form adjacency with the designated router and no one else. Okay? As well as the backup as well. Don't forget that. So when we have the designated router, we also elect the second most important router, which is the backup designated router. So in case the designated router fails, we already have the backup designated router ready to go and it's still forming adjacency with all the other routers. And if you guys remember, a router which is not a designated router, not a backup designated router, that is a draughter. Okay? Draughter, that's the terminology. Okay, so the LSA type 2 will basically inform about the network type, and it will inform the other routers if an election is necessary. We also do have the type 3 and type 4 LSAs. They are both summary LSAs. The difference between the 3 and the 4 is that the 3 will be between different areas. So the 3 will be for when you want to inject the networks from one area into another. The 3 will be the LSAs that will be sent from one area to area 0 so that they can be advertised to different areas. And we also do have the type 5 external LSAs. The type 5 external LSAs, they will just basically contain information of how to get to external networks. Okay? So you expect to find LSA type 5s when we have an autonomous system border router or we have an exit outside of the OSPF routing domain that we have. Okay. LSAs, they individually act as a database record and they provide specific OSPF network details. LSAs in combination describe the entire topology of the OSPF network or area, and any implementation of multi-area must support the first 5 LSAs. If it doesn't support the first 5 LSAs, there is no way we can have the multi-area OSPF because they will not be able to advertise networks between different areas. Now, the LSAs that we see there in the bottom, 6, 7, 8, 9, 10, 11, they're all used in OSPF version 3. Some of them are not even supported by Cisco, and that's why we don't even talk about them too much. Talking about the other LSAs, 6 up to 11, is a more advanced networking course. So that would be more for a CCNP level of study. All right, so let's move on. OSPF LSA type 1, just as we described. So how do we see this in the topology? So type 1 will be between all the routers. So within the area, all the routers that belong to a certain area, they will be exchanging information about the networks inside of the area. And as we can see here, on every single one of these areas in this design, we do have type 1 LSAs everywhere. Right? So we do have 2 area border routers here, ABR1 and ABR2. And why are they ABRs? Because they are in the boundary of 2 different networks, different areas, sorry. And area border router 2, the same thing. It's in the border of area 0 and area 2. That's why it's known as ABR. And we do have an ASBR here. Now, look at this. The ASBR doesn't actually have to be connected to area 0 because the ASBR is actually a way out of the OSPF routing domain. How about the LSA type 2? Now, LSA type 2, they have the following characteristics. They are only found in multi-access and non-broadcast multi-access. And if you remember what that is, it's just basically wherever we have an election. Remember the election? Now, we don't have election in a point-to-point, and that's why here in the serial connections, we don't have the type 2 LSAs. Okay? Because after all, we don't even have an election here. We do have elections where we have a gigabit Ethernet connection by default that is considered to be a multi-access or non-broadcast multi-access network. And that's why it requires an election. And that is why it will have the type 2 LSAs. Now, they also refer, yep.
Just a quick question. In area 2, we don't have the type 2 there because you said it point between two routers, right?
Yes.
But because it's just a connection between one router to the other and then the second one to the third one, it's point to point, so we don't have a multi-access network, right?
No, that's more related, Shai, to the technology of the interface. It's not much related to the amount of devices, because here we only have a direct connection, right? So
Yes.
these may look like a point to point, but in reality it's not, because it's a gigabit connection. So this gigabit connection can be connected directly to another device, but it doesn't necessarily have to be. Now, with the serial connections, they have to be between two terminations. And that's why they are point to point. They are point to point connections by default. So by default, the serial connections, they are all point to point network types. And that's why we don't have an election by default. Now, with the gigabit Ethernets, even though we just have one single connection, the network type by default is considered to be a broadcast. And that's why we need to have an election here. Even though it's just one single connection, it will still require an election. Okay, so it's more associated to the interface type itself, the technology of the interface. Is that clear?
Yeah, thank you.
Awesome. All right. How about the LSA type 3s? The type 3s, as I already discussed with you guys, they are used by the area border routers only to advertise the networks from different areas. So they are going to exist in the ABRs. So let's see if you guys agree with me, but ABR number 1 needs to find a way to inject all the routes that it learns in area 1. And how does it do that? It will send an LSA type 3 to area 0. So the other routers in area 0, they will receive these LSA type 3 and then send it to their area. Okay? And the process repeats itself until ABR1 learns about the networks and until ABR2 learns about the networks in different areas as well. So the area border router creates a type 3 LSA for each of its learned OSPF networks. The area border router flood type 3 from one area to another area, as we just discussed. How about the type 4s? Now, the type 4s, they are associated with the ASPR. Okay, so let's do a quick recap. We have LSA type 1, which is associated to the area itself, and it's to advertise the networks within the area. We have LSA type 2, which is used for the network type. So whenever we need to have a designated router, backup designated router, or we don't have to have it, we are talking about these type 2 LSAs. Type 3 LSAs, they are in the ABRs. They are used to advertise the networks from one area into another area. And now we're talking about the type 4 LSA, which is associated to the ASBR, right? So now, the type 4 LSA is sent outside the area where we don't have the ASBR, and it tells the other routers, all the other routers, how to get to the ASBR. Okay? That's the only purpose of the type 4 LSA. Tell everybody how to get to me. Okay? That's the purpose of the type 4 LSA. So ABR1 already knows that the ASBI is in the same area as it. So it doesn't have to receive a type 4 LSA from the ASBI. Now that ABR1 knows that there is an ASPR because it will receive the routes, okay, as external OSPF routes, it already knows where the ASPR is. It already knows how to get to the ASPR, but it needs to tell everybody else where the ASPR is and how to get there. And how does it do that? By sending the type 4 LSAs to everybody else. Right? So this is the purpose of the type 4 LSA. Now we're only left with type 5 LSAs. Now, type 5 LSAs, they will be the information of where the external route is. So do not get confused between LSA type 4 and 5. I actually like to explain type 5 before 4, but it may be confusing, so that's why I decided to follow the order. Now, the 5 will be coming from the SPR. So the ASPR sending the information of where the external route is outside of the OSPF domain. So as we can clearly see here, ASPR has a route to the internet. And how does it let everybody knows about it, including the ABI in the same area as it? Sending the type 5 LSA. Type 5 LSAs, they're exclusively used to advertise external network addresses. So they will be coming from the ASPR. The type 4 LSAs, guys, they are not coming directly from the ASPR. They are coming from a router that learned the ASPR. Right? So this is the major difference between the type 4 and the type 5s. So a quick review. Type 1, they are the network, the router LSAs. They are basically within the same area, talking about all the networks, all the links within a specific area. Type 2, associated with the network type. If it's a point-to-point, if it's a broadcast, associated to the type of the interface to actually find out if we require an election to happen, this is going to be type 2 LSAs. Type 3 LSAs to send information from one area to another area. Type 4 LSAs, it lets everyone else know how to get to the ASPR. And type 5 comes directly from the ASPR, telling where the route to the external network is located. That's it. These are all the LSA types we have in OSPF. Now, this is a key thing for us to understand and get us our minds around how OSPF actually works. Now, in Netacad, we don't go too much deep into LSA types because it is considered to be an advanced topic. Now, in Netacad, I think you guys get like probably 1 or 2 questions specifically about LSA types, right? Okay, so how about the commands to verify the routes that we learned via OSPF? So if you remember how the routing table displays the OSPF learned routes, we have O, OIA, and OE, right? So what does each one of these means? The simple O, just the O, is a network that was learned from the same area that the router participates. This is just a standard O. The OIA is OSPF inter area. Inter. So every time you see this inter, do you guys know a word international? So people coming from a different nationality, okay? From another country. So inter, from a different area. All right, so OSPF inter area. We also have OSPF intra area, which is the standard O. So the standard O, intra area, because it's coming from the same area that the router is part of. The inter, from outside of the area. Now, in regards of the routing table and the administrative distance, they are the same. So it doesn't matter if it's external OSPF, intra-area, inter-area, they all have the same administrative distance, which is 110. So please remember that the square brackets in the routing table, they display two things. The first thing to the right, to the left, sorry, is the administrative distance. And we have a slash right in the middle, and everything displayed to the right inside of the square brackets is the, anyone know? We do have the administrative distance to the left. What is this thing? Is the
Cost.
For OSPF is cost, but it's metric. Yeah, so it's metric cost. Yeah, all right. So for OSPF, because the metric is the cost, you can say it's the cost. That's totally fine, right? Now, these are the intra area, the ones in green with just a standard O, and the IA inter area, they're coming from a different area. And we do have these weird thing here, O asterisks E2. Anyone have any idea what that is? OE2. So intra,
External from
inter,
the ASBR.
exactly, external. So the E is for external route. So if you guys remember the asterisk, what's the asterisks? The asterisk is actually telling us that a default route, okay, has been injected, has been distributed. So the O asterisk is telling us it's a default route being redistributed into OSPF. And the E, it's because it's an external route. It's coming from outside of the OSPF domain. All right. And it has a metric of 1. Does anyone know why it has a metric of 1 or cost of 1? Because remember that the default route is created with a static command. So you create the default route with usually a static default route. Okay? And that's why it shows as metric 1. We do have OE1 and OE2. And oh my God, what is the difference? I will tell you what the difference is. So by default, all the routes that are coming from outside, all the external routes, they are external type 2. And what does that mean is the distance to the ASPR doesn't matter. So the metric to the ASPR doesn't matter, doesn't go to the calculation. Now, when we add the metric to the ASPR, including the metric to the network, we have cumulative metric because we're adding up the cost to the ASPR plus the cost from the ASPR to the route. That is an external type 1, OE1. By default, all of them are external type 2, but I'm just telling you guys the difference because you may come across the type 1 someday in your life. And now you know what's the difference. So the external type 1 is a bit more accurate than the external type 2. The external type 2 will just have the metric containing the metric information to the network. And it's not considering that in order for us to get to the ASPR, there is also a cost involved. Okay, so if it's OE2, it doesn't care. If it's OE1, it will take in account that in order for us to get to the ASPR, there is a cost associated to it. All right, it's steps to OSPF convergence. The order in which the best paths are calculated is as follows. All routes calculate the best path or paths to destinations within their area. Okay? Remember that the area is like a boundary for the LSTBs. It's like a boundary for the calculations. That is why. These are all type 1 and type 2 LSAs. All routes calculate the best path or best paths to other areas within the inter-networks. So if they're doing that based on information from an ABR, as we already discussed, that is considered to be an inter-area because it's coming from a different area. All routes calculate the best path or paths to the external autonomous system. We already talked about OE1 and OE2. All right, so we finished discussing how it works and the LSA types and the terminology, the ABR, ASBR. Now we are going to talk about how to configure it. There are basically 4 steps involved in implementing multi-area OSPF. The first step is to gather the network requirements and parameters. And by requirements, it basically means which interface of the router belongs to an area, which other interface belongs to a different area, and so on. Our second step is to define the parameters. Are we going to use multi-area? Are we going to use single area? What is the IP addressing plan? What are the areas if there are multi-areas? What is the network topology? If we are configuring broadcast and non-broadcast, who is going to be the designated router? Who is not going to be the designated router? All of this is important. In step number 3, configure the multi-area OSPF implementation based on the parameters and verify the multi-area implementation. Let's get down to an example. This is an example of how we configure multi-area OSPF version 2. So we do have 3 routers in this topology. Router 1 to the left bottom side, router 3 right hand bottom side, and router 2 at the top. So we're going to establish neighborships between these routers, and we are going to exchange the routes. Now, router 1 by default only knows about the networks that are directly connected to it. Router 3 only knows about the networks that are directly connected to it. Now, how many area border routers do we have in this topology? Anybody? Anybody? So a few people saying 2. Does anybody wants to say 3? And if 3, why? Anyone? Give it a go. Try. Anyone?
So did you say how many networks?
How many area border routers? How many ABRs?
Oh, I said 2.
2, 3? Who thinks it's 1? Okay. So it's 2, right? Because look at the definition here. A router becomes an ABR when it has 2 network statements in different areas. One example, router 1. Please note that the interfaces, the LAN interfaces of router 1, which include gigabit 00 and gigabit 01, they are in area 1. Now, the interface of router 1, which is stereo interface 000, it does not belong to area 1. It belongs to area 0. So when we do the configuration in router 1, we'll note that the networks that belong to area 1, they are here at the top. At the bottom, we have the network that belongs to area 0. So there you go. This router 1 is an area border router. It has it has a few networks in one area, a few other networks in area 0. And that's how we determine what is an area border router. So router 3 is pretty much the same. It's also an area border router. How about configuring OSPF v3? So you guys remember when we talk about OSPF v3, we are relying on IPv6 unicast routing. So all of these commands, they're considering that we already issued the command IPv6 unicast routing. And please remember that in order for us to make OSPF version 3 work, we need to assign the linked local addresses as well, because OSPF version 3 communicates using linked local addresses. And please remember that when we assign the networks to OSPF in OSPF version 3, we actually doing in an interface by interface basis. So we don't have the network command in OSPF version 3. Please remember this, right? This is the exact same topology. So we still have two ABRs here, which is router 1 and router 3. Now let's recall the commands. So we basically create the OSPF version 3 with the command IPv6 router OSPF. We assign the router ID. Now, can anyone tell me what is going to happen here in this scenario if I do not assign the router ID? Does anyone remember what happens here if I forget to assign the router ID? Is this still going to work? It will tell you that you need to assign because you don't have any IPv4 interface. If you had any IPv4 interface on the routers, the router will be able to assign itself a router ID, which would be the highest IPv4 address of the loopback interface, if there's any loopback interface. If there are no loopback interface, it will be the highest IPv4 address of any physical interface. Okay?
Robert,
yes, John?
just if you can skip back 2 slides,
Yep.
just to the IP4. Another one back.
Yep.
So when you advertise the networks in the commands, they use the method to write the IP address 10.1.1.1 and then the subnet 000. So can you remind me what does it mean? Does it mean that it advertises?
This is when you are advertising the network specifically connected to the interface that you are specifying. So this 10.1.1.1 is the interface IP address. So it's the IP address of the interface. So when you do this, you're basically saying that you want to advertise the LAN connected to this interface.
Okay, so I can, in that way, and I can also use the
network. Yes. So this is usually preferred, and you know why? Because you don't have to specify the wildcard mask.
Okay, yeah.
Remember that if you put the network instead, you will have to write network 10.1.1.0, and then you have to specify the wildcard mask. So you have to go, oh, this is /24, so /24 stubnet is 255.255.255.0. So the wildcard mask is 0.0.0.255. So sometimes it reduces the amount of effort if you just specify, I want to advertise the network connected to this interface. And then you specify the interface IP. So you don't need to specify the wildcard mask. Let me go back, which is the case here. All right.
Okay. Thank you.
No worries. Okay, so let's go back to where we left off. Now, these are the commands for us to verify the functionality of OSPF. Show IP OSPF neighbor will show all the neighbor connections, the adjacencies that we have. So it's going to show us who our friends are. All right. So it will show who are we talking to. Okay. So you know when you guys have Facebook and you have to, someone sends you an invitation and they want to be your friend and you confirm, and then now you're friends and then you are related in the social network. It's the same thing here. So OSPF, they will send hello messages, they will exchange the hello messages, and then they will decide that they want to become friends. It's like accepting the other router on Facebook. They will form an adjacency, okay? Friendship. Now, with the show IP OSPF neighbor, we're going to be able to see what are the neighbors in each one of the routers. So if I issue the show IP OSPF neighbor on router 1, how many neighbors do you guys expect me to see if I issue this command? Just one, right? There's just one connection here to router 2. So router 1 is only an adjacency. It's only adjacent to router 2. Now, how about router 2? If I issue the show IP OSPF neighbor, how many neighbors do you expect me to have on router 2? 2. All right. How about router 3? Just one. Okay. We do have the show IP OSPF command as well, which will show us valuable information about OSPF. We have the show IP OSPF interface that is going to show us interface details such as the hello timer on the interface, the dead timer on the interface, and so on. We also do have the show IP protocols. You guys remember when we talk about EIGRP, remember that this is my favorite command ever when I'm troubleshooting routing protocols, because it just shows us so much valuable information about the routing protocol itself. What is the routing protocol being used? What is the process ID if it's OSPF? If it's EIGRP, it's going to show us what's the autonomous system. It's going to show us what are the passive interfaces and so on. It's also going to show us the networks that we are advertising. So that's why the show IP protocols is just one of the most useful commands ever. We also have the show IP OSPF interface brief to show detailed information about the interface. The show IP route OSPF will show only the OSPF learned routes. It's just basically going to filter the routing table so that everything else gets out of the routing table, and it's only going to display whatever it is in the routing table that we learned through OSPF only. We also have the show IP OSPF database, which is pretty self-explanatory. If you want to see the LSDB, link state database on a router, show IP OSPF database will do the job. It will show you the link state database containing all the link state information for a certain route. And if you actually show the IP OSPF database, you can actually see which one is going to be installed in the routing table. Because remember that the calculations will be done and only the best route will be installed in the routing table. So if we go and do the show IP OSPF database, we'll see all the other options, all the other paths to a specific network, and not only the one that has won, not only the one that has been chosen. These are the outputs. Like I said, the show IP protocols. There you go, my preferred command of all times when troubleshooting routing. And it's just so much useful. It gives us so much information of something that we could possibly have done wrong. Now, this example here shows us the number of areas that this router is connected to. It shows us if there's any access control list filtering information. We have the router ID information as well. We have the information saying if it's an area border router, if it's an autonomous system border router, if it's just an internal router, it's going to tell us. It's also going to tell us what are the networks that we are currently advertising and which area we are advertising them. It's also going to show us where is it learning this information from. In other words, it's also going to show us the adjacency. All right, and the last time an update was received, and also the administrative distance. With the show IP OSPF interface brief, we will show more granular information about the interface itself. If you go back here a little bit, and the show IP protocols is going to tell us how many areas the router is part of. It's going to show us the network and the areas, but it's not going to show us if that area is going to require an election. It's not going to tell us the cost. but the show IP OSPF interface brief will, okay? And it's also going to show us the IP address as well, the mask, the area, and so on. With the show IP route, as we just discussed, it's going to show us only the entries in the routing table that were learned via OSPF. Very simple command, show IP route OSPF. It's extremely useful when we have a routing table which is too large and you have to keep scrolling down because you have too many networks and you have to find the ones that are OSPF. So if you don't want to do that, show IP route OSPF will do the job. Now, this pipe begin gateway is actually going to start displaying information where it says gateway. Okay? So it's going to start showing the output where it says gateway. If you just do a show IP route OSPF, not going to show any of this, only going to show the O's and the routes. This is how the link state database looked like. I know it's scary. I know it looks awful. You don't have to know everything about the link state database. You just have to know that it exists, and you just have to know that it contains the information advertised by other routers. How cool is that? You don't have to know exactly everything that is here. Oh, I need to know every single one of the codes. There is no need for that, all right? So in the OSPF database or the link state database, we have the areas, the advertisements coming from different neighbors, the age, the link ID, and so on. Okay. Now, based on this, the router will do the calculations. It will estimate the cost. It will determine what is the best path to a certain route. And that's it. How do we verify multi-area OSPF version 3? Very similar to the way that we do OSPF version 2. We have to replace every time that we set IP for IPv6, and pretty much all the commands will work as expected. For example, the show IP protocols will become show IPv6 protocols. The information displayed is similar. The show IP OSPF interface is going to be show IPv6 OSPF interface. The output is also very similar. It's going to tell us the network type and so on. With the show IPv6 route, very similar to the show IPv6 show IP route OSPF. There is one packet tracer activity for you guys to do, configuring multi-area OSPF version 2. I have done a similar activity last week in the Cisco lab. So if you've got a chance, make sure you watch it again. Try to do the activity as well. It's going to give you a very good grasp on how to configure it, how to verify it, and so on. One more activity. Now, this activity is very similar. The only difference is that this one is OSPF version 3 instead of version 2. There's one more lab as well, configuring multi-area OSPF version 2. One more. And this is a chapter summary of everything we learned today. So we discussed and explained how multi-area OSPF operates in a small to medium-sized business networks. We talked about how to implement multi-area OSPF version 2 and version 3. We talked about the verification commands of OSPF version 2 and version 3. And that's all we had for today. Now, questions, guys. Now, this is extremely important that you guys get the point and how things work in OSPF. Because otherwise it's going to be much harder to configure it, to verify it, troubleshoot it. So make sure you understand the main concept of how it works. Now, does anyone wants me to go back to something that they didn't get it very well? And anyone that wants me to go back a little bit, no issues at all. Was that too fast, too slow? What do you guys think about the pace? What do you guys think about the pace? Is that good?